Okay, good day. This is Math 130, Intro to Statistics. I am Professor McCulley, and this is lesson number 7, Measures of Variation. So let's get to it. Today we're going to find the range of a data set. We kind of did that in the last lesson because of finding the mid-range. And then we're going to find the variance and standard deviation of a population. And as a sample, we're going to use the empirical rule to interpret standard deviation, and then we're going to approximate the standard deviation of a group data. So first off, some definitions. The range of a data set is the difference between the maximum and minimum entries in the data set. Note the data must be quantitative. And then the definition, deviation of a value in a population data set is the difference between the entry and the mean, which again is lowercase mu of the data set. So just as a real quick example, given the set weights given the set weights in pounds of 4 fish caught in, find the range and the deviation of each fish. Clearly this is a small sample, so we're just doing this out of convenience. So first, to find the range, we got to figure out what the max value is. Oops, I didn't want to do that, so let's close that up. We got to find what the maximum value is. So our max value for this particular one is clearly 10. Our minimum value is clearly 5. So our range is just the difference. 10 minus 5 gives me 5. All right. Then if we want to find the mean of that, we'll go to this. We'll add up what we were given. So 5 plus 7 plus 8 plus 10 equals 30 divided by 4 is 7.5. So our mean, and since this is a sample, we'll use x bar. Mean is 7.5. So the value and then the deviation for each of those values. So, and again, just reiterating, is the value minus the mean. And so since the value is 5, the deviation will be 5 minus 7.5, which is negative 2.5. And so the deviation is negative because the mean is more than the value. And then we have 7. So 7 minus 7.5 will give me 0.5. And then 8 minus 7.5 gives me 0.5. Oops, I made a mistake here. So 7 minus 7.5 should be negative 5. And then let's see here, 10 minus 7.5 is positive 2.5. So for 10. And so these are my values. These are the deviation for each of those values. Now individually, these don't say a whole lot for us, but standard deviation, which is something that we're going to be talking about, is based on these calculations. So moving on, the definition of population variance, the population variance of a population data set of n entries is, and so this is this symbol here is the lowercase Greek letter sigma. So this is a lowercase sigma, and if you remember, this symbol right here is the uppercase sigma. And so right here is the variance. And so what this is telling us to do is to calculate the variance of each data set, square that value, add them all up, and then divide by n. So the population standard deviation, and so the standard deviation of that is the square root of the variance. So if I take the square root of something squared, I just get that value. And so my population standard deviation is just the square root of this population variance. The sample variance and sample standard deviation are very similar, and they're just using s squared and s for those two values. The big difference that we find for this one is that when we do this value, it's n minus 1, and whereas in the population variance and the population standard deviation, we use the entire value n. So if our population was 15, we'd use 15. but when we're doing standard deviation of a sample, if our n was 15, we'd use 14. And the book only gives us the statement that when calculating a statistic to estimate a parameter using n-1 provides a better estimate. I think what it is because when you divide by a smaller number, you get a bigger value, so it makes that standard deviation just slightly larger to include more values. All right, so let's move on here. Use your graphing calculator and the first variable stats on the following sample of full-grown heights of corn plants measured in centimeters. And so what we're going to do here is we're going to grab our graphing calculator, and there's a lot of things that are in the first variable stats, and so it's worth us taking the time to go through it and see all of the things that are in that first variable stats. So we're going to use the stat button, so I want to hit stat, and the first thing we always want to do whenever we're starting a new problem is we want to clear out that we're going to enter some data. Is we're going to clear out those lists. So the first thing I'm going to do is I'm going to hit 4, and I'm going to hit second, and then L1. We're only going to have one list in this particular one. I hit enter, and we're done. So then I hit stat again, and then we're going to edit, and so you'll notice I have some values left over from a previous. I think I'm actually going to use them later, but that's okay. So I'm going to enter this data set into the value, and we're going to talk about what the first variable stats give us, even though we've kind of done this once before. All right, so my data set was 204, and then the next value was 206, and the next one was 210, and then it was also 210, and then it was 213. Oops, that's not 213. 213, and then 207, and then 209, and then 211, and then 208, and then 207, and then let's see here, 212, and then 211, and then 219, and 211 again, 210, and we finish off with 205. And so if I go back here and I look, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8 times 2 is 16. I've got 16 pieces of data. Just a real quick check. The 8th piece was 11. That looks right to me. Okay. So I think I've got them all entered in correctly. I'm sure you'll correct me if I'm wrong. And so here's what I'm going to do. I'm going to hit my stat. We're going to go over to calculate again. We're going to hit the first variable stats. So I'm going to hit 1. And we want to make sure that the frequency list is empty. And if you have something there, you can just go down to it and hit the delete button, and it'll clear that out. But we do want L1 in our list, so we will bop down, we'll have it calculate. And so let's go over what all of these values actually mean. All right, so first off, we have X bar is going to be 209.5625, and this is the sample mean. But since you calculate it the same way as a population, we'll also call it the population mean, even though the calculator doesn't do two different ones. And again, the only one that's going to be different is going to be the population variance, and the difference between the population variance and the sample variance, as well as the population standard deviation and sample standard deviation. The next one was the sum of the x's, and that turned out to be 3,353. So this is the sum of the x values. So this 3,353, if I were to add all of these values up, that would be the sum. The next one is what's called the sum of squares, and that turns out to be 702,857. And so this calculation, so this is the sum of squares. And so if I squared all 16 of these values and then added them up, I get this 702,000 value. The next one, S sub x equaling the 3.5957. That thing right there is our sample standard deviation. And then we have lowercase sigma, 3.4815. This is the population standard deviation. Oops, I need to spell right. Let's do it correct. So I need standard, P-O-P-U-L-A-T-I-O-N, standard. Did it again. And then the next one was n equal to 16, and this is just the number of elements. It just counts out how many of those are in there and gives you that value. Next, you get min x, and that ended up being 204 for this data set. And this is the minimum value in the set. And then the next one, it's Q1, and that turns out to be 207, and Q1 is the lower quartile, and we'll be using that later on. And MED, that next thing, was 210, and that is our median. And then the next one, Q3, was 211, that is our upper quartile. And then our max x, which was 219, this is the maximum value in the set. And so we'll be using this off and on throughout the semester, so it's worthwhile going through and seeing what everything means. All right, so now that we've talked about variance and standard deviation, let's talk about what we can use that and how we can interpret that. So interpreting standard deviation, a construction company is trying to determine which lumber yard has the most consistently cut lumber. A sample of 10 2x4s taken from 2 lumber yards, and the lengths are recorded. So these are all in inches, and so they've recorded all of these values. It took a sample of 10 in both of these. And we got, in both instances, we got the same mean, which is possible. It's not very likely, but it's possible. And it turns out that they're only 5/100ths away from the 60 inches that we were looking for. But the lumberyard from A, its standard deviation was only 4.17 or 0.417, and the yard B was 0.504. So what I can interpret from that is, based on this particular sample, this sample varies a little bit more than the sample for A. So if I were to be happy with my calculations here, I would say that I would probably choose to do my business with yard A, because that has a little bit less variance than in yard B. And when I'm building, if I'm running a construction company and I want to have all of my boards to fit and be exactly what I expect them to be when I'm building a wall or door or whatever, then certainly having a more consistent set of board lumber cuts would be better. And you might have an instance where having a larger standard deviation might be larger. All right, so that's what I wanted to say there. Let's move on. The empirical rule for data sets with approximately symmetric, bell-shaped, or some we'll also call normal distribution. The standard deviation has the following characteristics. Approximately 68% of the data lie within one standard deviation of the mean. Approximately 95% of the data lie within two standard deviations of the mean. And approximately 99.7% of the data lie within three standard deviations of the mean. So if you're within two standard deviations, we would say most of your data set, certainly file lies within two standard deviation, and almost every single one lies within three. And so we can make some interpretations about data sets that lie outside two standard deviations. And so here we look at a normal distribution. This kind of shows these values that we had given to us here, where we could say if all of the values lie underneath this curve, then clearly these two sections here, one standard deviation below and one standard deviation above, that would be most of the values, and it turns out to be about 68%. And then if I go out two standard deviations, and another one, two to the left and two to the right, this area here is approximately 95%. And so we have just a little bit to the left and a little bit to the right outside those two standard deviations. So we would say that the usual values in a data set lie within two standard deviations of the mean, while unusual values lie outside two standard deviations of the mean. And so if most of our values lie within that 4 standard deviation range, we can make some conclusions or some approximations based on this statement here. And so what we can say is we have this range rule of thumb for estimating standard deviation. And it states that generally the range of a normally distributed data set is approximately 4 times the standard deviation of the data. And that makes sense because clearly most of those data pieces should lie within those 4 standard deviations. And so we can make some conclusions and we can make some approximations. If the range is known to be 12, then the standard deviation could be approximated to be 3. And if we knew what the standard deviation was, and then say it was 2, then an approximation for the range would be 3. So if we know that the range is 12, the range is 4 times the standard deviation, so 12 divided by 4 gives me an approximation of 3. And if I know the standard deviation, the range is 4 times, so 2 times 4 will give me that 8. And then with that range rule of thumb, we can make some approximations. The average time a gym member works out is 54 minutes with a standard deviation of 15 minutes. Using the range rule of thumb, would it be considered unusual for a gym member to be in the gym for 120 minutes? Okay, so if I know that my my average, my mean, and I'm going to change my pen, my mean value is 54 minutes, and my standard deviation I suppose I could have used sigma for this, was 15, then my range would be 15 times 4, which is 60. So if I put out a number line here, and you don't have to do the number line, I'm just doing this as a visualization, then here my mean at 54, 2 standard deviations below and 2 standard deviations above is going to represent 95% of that data. So anything lying outside of that 95% we would call an unusual value. And since it's 60, that means there's going to be 30 on the left. I put 6. 30 on the left of the mean and 30 on the right of the mean, giving me a total from here to 60. And again, this is just an approximation. But 30 less than 54 would be 24, and 30 more than 54 would be 84. And so we want to know if you're in the gym for 120 minutes, well, that's somewhere way over here. So based on our range rule of thumb for estimating standard deviation, we could make a conclusion that says, yes, we estimate that it would be unusual for someone to be in the gym for 120 minutes. Well, that's all I got. So, our Marvel fun fact of the day is that the voice of Groot is played by Vin Diesel, pictured right here. And even though in the movies Groot only says, "I am Groot," Vin gets a special version of the script that reveals what Groot actually says so that he can add the proper inflection and emotion to the line. Well, that's all I got for today, folks. Have a good day. Bye.